Malaysia Airlines Flight 134's pilots are in a fatal situation as soon as they take off from Brisbane, Australia. The three devices that indicate their speed have all malfunctioned. As the pilots try to figure out what has gone wrong with their enormous aircraft, alarms ring throughout the cockpit. 215 people behind them are unaware of the peril they are in. Will they be able to return to the airport, or will they be among the hundreds of other travelers who have perished in this kind of crisis over the years? This is the horrifying tale of Flight 134 of Malaysia Airlines. At Brisbane International Airport in Australia, 215 passengers and 14 crew members boarded a Malaysia Airlines Airbus A330 late on July 18, 2018. They had an 8-hour trip to Kuala Lumpur, Malaysia. The pilots would, however, be put in a precarious predicament shortly after takeoff, one that would guarantee they would not reach Kuala Lumpur this evening. There was a flurry of activity outside the plane as the passengers settled in for the lengthy flight. Ground engineers were replenishing the engine oil, luggage handlers were loading the passenger bags, and refuelers had filled the plane's tanks with more than 50,000 kilograms of jet fuel. From the outside, this process seemed to be chaotic, yet each person had a specific job to play. The two pilots in the cockpit were getting the plane ready to take off while all of this was going on. A very seasoned skipper sat in the left seat. Before switching to the Airbus A330 a year ago, he had flown more than 10,000 hours on Boeing 737s and 747s during his stint with Malaysia Airlines, which began in 1993. Fresh to the Airbus, having flown the plane for little over 500 hours. The first officer, seated on his right, had almost 10 times the captain's flying hours on the A330 while having less total experience. Prior to receiving training to fly the A330 in 2011, the first officer began his career with Malaysia Airlines in 2009, flying the Boeing 737. Both pilots had gotten enough of sleep, and when they got their aircraft ready to take off, everything seemed normal. However, this exact routineness would give the captain and many other important individuals a false feeling of security on this particular night. Thank you. The pilot started the outside walk-around of the aircraft at 5 minutes to 11 that evening after descending the steps onto the runway. To make sure their aircraft was safe to fly, pilots performed this test before to each trip. As the name implies, it entails following a predetermined path around the aircraft while keeping an eye out for any unusual activity, such as leaky hydraulic lines, dents in the aircraft's skin, or excessively shallow tire threads. The captain took a light to aid with this examination since it was dark outside. These walk-arounds often yield nothing noteworthy, but on this particular night, the captain was in for a surprise. The pitot tubes were located on the left side of the aircraft's nose, just below his own cockpit glass, and they were covered tonight. To gauge an aircraft's speed in the air, hollow cylinders, called pitot tubes, protrude from the side. There are 3 of them. One for the captain, one for the first officer, and one backup, because they are among the most crucial instruments on the whole aircraft. In the event that they are obstructed, pilots are unable to determine their speed, which may be lethal in airplanes. Over the years, hundreds of passengers have died as a result of blocked pitot tubes. However, in Brisbane, it is common practice for ground staff to intentionally block the pitot tubes while an aircraft is on the ground. The reason for this is because mud wasps, a kind of bug found in Brisbane, build their nests in precisely these types of buildings. Actually, there have been some severe cases with mud wasps aboard passenger planes. When Flight 134 drew up at the gate earlier in the evening, ground technicians in Brisbane covered his pitot tubes. Due to his contact with ground crew and uncertainty over who was responsible for removing these covers, they hadn't been taken off by the time the captain was doing his walk-around. The captain now had the task of finding them. There should have been no issue with this. After all, one of the most crucial aspects of the walk-around is making sure the pitot tubes are clear. However, while the captain navigated the airplane for whatever reason, he didn't seem to see these bright red coverings on the pitot tubes with his illumination. This still photo from the CCTV camera shows him briefly shining his light on the pitot tubes before continuing. It was as if he just failed to notice that these essential tools were protected. Now the scene was set for catastrophe. The first officer, meantime, was up in the cockpit, programming the flight path into the flight management computer and making sure the weights of the aircraft and the fuel were within safe bounds. He was unaware that a fatal error was being made just underneath him. As the chosen pilot for the night's flight to Kuala Lumpur, he was going to take command of one of the most damaged airplanes he had ever been required to fly. The captain ascended the stairs and returned to the cockpit around 90 seconds after starting the walk-around. After completing their last inspections, both pilots asked for permission to push back from the gate. That evening, aircraft 134 pushed back at 20 minutes after 11. Despite the imminence of disaster, there was one more opportunity for someone to discover that the pitot tubes were covered. The dispatch coordinator who accompanied the aircraft on the pushback was supposed to do a last exterior inspection of the aircraft as part of his job. However, he believed that the maintenance engineer had already completed this task this evening. Before the pilots taxied out to the runway, it was his last responsibility to show them that the nose wheel steering pin had been removed from the nose wheel assembly. The dispatch coordinator had just overlooked the pitot tubes, which are clearly visible here. The pilots were blissfully oblivious that all three of their pitot tubes were covered immediately outside their cockpit windows as they taxied down to runway 01. These pilots were about to unintentionally become part of a regrettable group of flight crews who had encountered a similar issue throughout the years, many of whom did not survive to tell the story. Like them, the 215 passengers in the back had no idea how dangerous they were. The first officer started the engines for departure at 25 minutes after 11 o'clock. The enormous jet started to speed up, but the first indication of problems appeared only a few seconds after takeoff power was applied. As the plane reached 50 knots, or around 90 kmph, the pilot became aware that there was no speed readout on his main flying display. During takeoff, everything happens very rapidly, and pilots have just a few seconds to choose whether to halt the aircraft on the runway before there is no more space and they must take off. The odd circumstances were just now starting to sink in for the pilots. Sight when the aircraft's speed exceeded 100 knots, or around 180 kilometers per hour. The captain glanced at the ground speed indicator and yelled out 100 knots, which is usual practice since pilots are urged to be go-minded. That is, to lean more toward taking off than aborting, beyond this speed. There was not much time left. "Ed," said the first officer, "then abort." Huh. This was a pivotal moment. Now, the pilots had seconds to decide whether to proceed with the takeoff or cancel it. Neither was excellent at their pace, but which was superior? The captain pointed out the broken speed tape to his first officer once again. This was as good a moment as any to cancel the takeoff. However, the pilots went on. The first officer advised them to fly to 80 or 3 in a desperate attempt to achieve a consistent airspeed to appear on their instruments. By obtaining an airspeed measurement from an alternative pitot tube, he thought that would be able to get a trustworthy airspeed indicator. However, he was unaware that all 3 tubes were clogged. The plane had accelerated beyond the point of no return in a matter of seconds. The runway was rapidly coming to an end. Now, the pilots were determined to execute the riskiest takeoff of their professional lives. Unaware of their speed, they were about to launch a fully loaded passenger plane into the sky. The aircraft's nose began to rise as the first officer started to draw back on his side stick. Now that the jet was in the air, it began alerting the pilots to danger right away. When the master warning chime went off, it meant that there was a significant problem that the pilots needed to address right away. Since the aircraft couldn't manage its speed by adjusting its engine power without knowing how fast it was traveling, the autothrust disconnected. Recognizing this, the first officer maintained the thrust lever at maximum continuous thrust, which gave the engines the highest power they could maintain for long stretches of time. Preventing an aerodynamic stall was his first objective now that he was in the air. When an aircraft just can't fly fast enough to stay in the air, this happens. The first officer's aircraft would just drop out of the sky if he allowed it to become too sluggish. The pilots, however, lost the chance to perform a crucial operation at this moment. They did not follow the unreliable speed indicator protocol, even though they had recognized that their speed indications were malfunctioning. The pilots were expected to do some tasks from memory rather than using checklists as part of this process. This is because they needed to avoid wasting valuable time searching for the right checklist since their situation was so urgent. Whatever safety margin the pilots had was now eroding. Crucially, this was true. This process included raising the nose up to 15 degrees and pushing the engines to their highest setting, sometimes referred to as toga thrust or takeoff go-around thrust. This would guarantee that the aircraft ascended safely without stalling or losing speed. The pilots were lower and slower than they would have liked to be since they didn't think to follow this technique. Once again, the first officer turned to troubleshooting. He was looking for any indicator of the plane's speed. In order to change which pilot tube was supplying his instruments with airspeed data, he once again requested that the captain set the air data reference switch to 3. The first officer reasoned that it was almost unlikely for all 3 pilot tubes to be clogged, but it was feasible for 1 or 2 to be. But that's precisely what happened to them. Despite moving this changeover to ADR3, the pilot's instruments remained same. Their instruments showed a speed that was entirely fictitious. A fresh alert appeared on the pilot's instruments just when they believed that things couldn't get much worse. They were informed that their aircraft had entered the so-called alternative law. Airbus uses the phrase alternate law to describe a significantly reduced level of automation that the aircraft reverts to in the event that certain systems malfunction. In this instance, the plane's stall protection was lost due to the lack of airspeed data. Because it prevents pilots from positioning the aircraft in a way that may cause it to enter an aerodynamic stall, this is an essential piece of technology in an Airbus. Ironically, the pilots had a higher chance than ever of stalling the airplane in the absence of airspeed information. They had lost it just when they needed stall protection the most. Now the strain on the pilots was tremendous. They had no clue how fast they were flying, and they were rising into thinner air at night. Furthermore, they had lost the automated safeguards that would have prevented them from placing their aircraft in a risky situation. Now, in the midst of warning bells and sirens, the 2 pilots had to decide what to do. Over the following 5 minutes, the decisions made by 215 passengers would determine their fate. Air traffic control had not yet been informed of their predicament. Pilots are instructed to prioritize piloting the aircraft, followed by navigation, and finally communication without traffic control in the event of an emergency. The words aviate, navigate, communicate encapsulate this. The pilots were instructed to change to the departure frequency by the controller. Interconnect departures with Enlation 134. Please provide frequency for Enlation 134. Decimal 4 to 5, 118. 118, 1 to 30, and 5 minutes. However, the captain neglected to change his radio to the new frequency in the midst of the chaos. A pan-pan signal, which is 1 step short of a declaration of emergency, was then sent to air traffic control by the first officer. However, this communication was ignored. The tower controller wasn't anticipating another call from the flight, and the plane's radio was still set on the tower frequency. A few seconds would pass before this miscommunication was cleared up. The captain found the faulty speed indication technique that the first officer had requested. At last, the team was starting to tackle their issue in a methodical manner. After that, the first officer informed the departure controller of their predicament. On their current heading, the pilots were now authorized to ascend to 10,000 feet. They would have time to troubleshoot their problems as a result. However, operating a plane by hand without any speed indicators is a very exhausting experience. Since it was night, and he couldn't see out the window to check his speed or location in relation to the horizon, the first officer's entire focus was on making sure he was operating the aircraft safely. All he could do was depend on the instruments before him. The audio recorder in the cockpit detected both pilots' elevated respiration rates due to the high level of strain. In order for them to fix the issue jointly, the captain was keen to reduce the first officer's burden. After all, the first officer spent almost 10 times as many hours on the A330. His background would be very helpful in handling this circumstance. In order to concentrate on resolving the issue, the captain requested that the first officer switch on the autopilot. However, the first officer informed him that this was not feasible. The autopilot could not operate the airplane without an indication of airspeed. In order to solve this issue and return the aircraft to Brisbane, the pilots would need to operate the aircraft by hand. It was regular practice at Malaysia Airlines for the captain to take control of the aircraft in an emergency. However, the pilot chose not to follow this protocol on this particular trip. He was aware that the first officer was much more experienced in flying the A330 and that this was the best use of his time. The captain concentrated on handling the issue and making judgments about the flight, even though he was prepared to pilot the A330. Excellent crew resource management was shown by allowing the first officer to continue piloting the aircraft. It made certain that he and the first officer were both using their advantages. The pilot started using the unreliable speed indication technique as the aircraft ascended. This required maintaining the nose between 9 and 12 degrees above the horizon and setting the engines to maximum continuous thrust. Airbus had discovered during flight testing that this thrust-pitch combination would guarantee that the aircraft continued to ascend at a safe pace. The situation has finally stabilized for the team. They had their plane under control and were methodically resolving its issues. However, they faced a formidable challenge. They had begun flying, but now they would have to coordinate their return while securely navigating back to the airfield. Control of air traffic. The first officer requested air traffic control if he could rise to 15,000 feet when the jet got close to 10,000 feet. Increasing the space between themselves and the Earth was always a good idea under their circumstances. As the plane soared, the captain, who was the first officer piloting the aircraft, shouted out the necessary pitch and power settings to maintain the aircraft within safe bounds. At one point, however, the first officer instructed the captain to stop this process so he could concentrate on piloting the aircraft. Once again, this demonstrated how well the pilots handled the situation. They had the right priorities in place. They had to pilot the aircraft first and foremost. At 11,000 feet, the first officer stabilized the aircraft at this moment. The crew was starting to realize that they may not be able to get their airspeed indicators to function. They would have more time to make a mistake that may bring down their aircraft the longer they were in the air. It was time for them to go back to Brisbane. In order to return to the airport, the first officer requested that air traffic control guide him. After that, the crew went back to using the faulty speed indicator method. They would have no trouble getting back to the airport if they could get any of their airspeed indicators to function. They performed this process by switching the air data switch between its 3 settings, each of which use airspeed information from a separate pitot tube: the standby, the first officers, or the captain's. The first officer informed the captain of which air data system was supplying data to which cockpit display and what speeds they were showing each time the pilots changed the air data source. It was hoped that at least one of the pitot tubes would provide them with an airspeed indicator that seemed realistic. The pilots were still unable to get a reliable indicator of airspeed, however, even after repeatedly alternating between the 3 positions. Their morale was severely damaged by this. It seemed that they would never be able to get their speed indicators to function. In the absence of speed indicators, They were forced to use the pitch and power setting charts that Airbus had supplied and depend on the hope that they would keep them flying at a safe pace while they troubleshooted the issue. The pilots ultimately arrived to a step in the process that they believed they would never need to utilize since solution after solution failed. They were now required by protocol to turn off all 3 air data computers. This is unimaginable on a regular flight. Among other crucial bits of information, the air data computers provide the pilots and the aircraft's computers information on the aircraft's location, altitude, and velocity. The airplane would be severely disabled if these systems were turned off. Even worse, disabling the ADRs is a permanent change. The pilots could not go back if they did it. However, as we'll see in a minute, there was one significant advantage to doing this. However, the pilots chose to trade positions to ensure that shutting down the systems was the correct course of action. The captain was given command of the aircraft by the first officer, who also instructed him on the thrust and pitch settings he had been utilizing to maintain safe flight. The first officer took the checklists from the captain and started going over the faulty speed indication method on his own. By taking turns, each pilot could now correct the other's faults before executing the last, irrevocable step of turning off the air data processors. The pilots contacted air traffic control after the first officer had completed the process and reached the same result as the captain. The pilots requested air traffic control if they could fly between 10,000 and 12,000 feet instead of staying at 11,000 feet, since they knew that turning off the ADRs would result in their losing their altitude information and having to depend on the less precise GPS to estimate their height. When flying manually, this would provide them some leeway and offer them a buffer in case their altitude measurements were off. On the checklists, the pilots had now reached the point of no return after switching responsibilities. All ADRs would need to be disabled. To let both pilots know what to anticipate, the first officer went over every item on the checklist before executing it. He then turned off all 3 of the AirDet PCs at about 15 minutes before midnight. Disabling the ADORs has a huge advantage in addition to serious drawbacks. On the bus or backup speed system, a fresh visual appeared instantly. For precisely this kind of situation, Malaysia Airlines has requested that Airbus install this equipment in its A330s at a cost of $300,000 per aircraft. It gave the pilots a clear and immediate indicator of their airspeed. It operated cleverly by using angle of attack sensors, which are likewise found on the aircraft's nose, rather of the occluded pitot tubes. As a result, the backup speed scale was unable to provide pilots with an exact airspeed figure, but it could provide them with an approximate indication of whether their speed was too high or too low. The pilots would be safe as long as they remained in the green zone. The crew's workload was greatly decreased as a result. As of right now, they have been studying performance charts to figure out the proper engine settings and pitch attitude. This was all they could do and hope for the best. However, they could now see in real time whether they were operating the aircraft at a safe pace. Flight 134's situation was beginning to improve. The pilots requested air traffic control if they could give them a speed indicator over the ground just to be sure. Even though it wouldn't precisely match their speeds, this would offer them a ballpark estimate and let them verify the backup speed system's readings. 210 knots was ideal, but there was still more problems ahead. The aircraft was reduced to a considerably simpler flying machine when all 3 air data processors were disabled, and certain critical systems were unable to function. The wing spoilers, which slow the aircraft down as it lands, weren't functioning. As a result, after landing, the aircraft would need a lot longer runway than usual. Furthermore, the jet would be landing 24,000 pounds above its maximum landing weight if it were loaded with a lot of fuel. Although this meant that the pilots would have to make sure they landed softly, it also meant that they would need to utilize a lot more runway. In light of the urgency of their position, the pilots decided that it would be safer to land now, even if it meant landing overweight, even if they could dump part of their gasoline over the water. To make matters more complicated, the pilots would have to let the landing gear fall using gravity alone since the standard hydraulically powered approach had ceased functioning. Following their discussion of these restrictions, the pilots started getting the aircraft ready for landing. The captain called air traffic control to ask for permission to descend after the first officer informed the manager of the cabin crew of their predicament. While continuing to prepare for the landing in Brisbane, the pilots started descending to 7,000 feet. To make their approach as steady and predictable as possible, they aimed to align up with the runway from a considerable distance out. Air traffic control, meanwhile, assisted by giving the crew their ground speed. The pilots were comfortable that they were operating inside safe bounds as a result. The pilots had some time to go over the approach and landing procedure step by step as they headed back towards the airport. On the last approach, they wanted to avoid any shocks. Aside from their weight and the non-functioning wing spoilers, they were aware that the nose landing gear steering was broken, which would be a problem when they landed. When they shut down the air data computers, they also deactivated this. They would have to control the aircraft on landing using only the rudder if they didn't have nose wheel steering. They would also be unable to divert the jet off course and back to the gate after it came to a halt on the runway. After landing, the pilots informed air traffic control that they would need a tug to return them to the gate. And after landing on Malaysia 134, we could need a tug. Yes, and because of a nose wheel steering loss, we need a pull after landing. Malaysia 134 is a copy. We'll make it happen. Additionally, do you know how long it will be until you return to the aerodrome? Before stabilizing, Malaysia 134, we may tolerate lower altitude thrust before being prepared for the approach. Malaysia 134, I get it. I'll put you on vectors back to the airfield if you agree. If you need it, I can give you runway 19. Since we have plans for runway 01, and we want to establish radar with this, sir, we will continue to utilize it. We may now continue using the descent relation 134. Roger, Malaysia 134, descend to 5,000, then bear right on 210. Right direction 210, please, descent 5,000 and 134. The crew started to maneuver southwest, almost parallel to the runway, after continuing their fall to 5,000 feet. From their location, they could see the airport on this clear night. All the passengers in the rear knew was that there was a problem with the aircraft and that they would be heading back to Brisbane. They were unaware of the gravity of their predicament. The crew started preparing their approach with the controller while air traffic control continued to inform them of their ground speed. The pilots started talking about what they would do in the event that they had to execute a missed approach, now that they had essentially planned the approach and landing. Even in the best of circumstances, this is a high workload technique, but the pilots would need to carefully plan it since they would only have an approximate idea of their airspeed. They felt it would be better to have air traffic control verify that they were truly at 4,000 feet when they leveled out, according to their GPS. Typically, controllers can determine an aircraft's height since the aircraft communicate this information to the ground via their transponders. However, Flight 134 was not communicating an altitude to air traffic control since its standard systems were malfunctioning. All the pilots could do was hope their instruments were showing the right altitude. The pilots finally lined up at the runway after air traffic control sent them vectors. Fortunately, the visibility was so superb that they could see it from around 40 kilometers away from the airport. As he approached, the first officer started to descend down the runway as the captain kept a watchful eye on the flight path. The pilots used the gravity gear extension lever to extend the landing gear when it was time. They were relieved that everything went according to plan and that the equipment locked into place. The first officer was totally concentrated on maintaining the aircraft speed inside the green range on his primary flight monitor, as they were now only minutes away from landing. This would undoubtedly be the hardest landing he has ever made in his career. He didn't know his airspeed. His aircraft was overweight, and the nose-wheel steering and ground spoilers weren't functioning. As he got closer to the runway, the pressure increased, only to provide an additional degree of safety. For traffic control was requested by the first officer to alert him if his speed dropped too low. If the speed falls below 130 knots, I would like it if you could notify us. I will render for you to set ground speed in the situation. I'll notify you if it falls below 130 knots. Malaysian 134 is equivalent to 160 knots on the ground. The controller then gave the go-ahead for the flight to land at midnight, when it was around 8 kilometers from the runway. Malaysian 134. There is no breeze on the ground. Runway 01 has been approved for landing. By now, the pilots had tried everything they could think of. Now all they had to do was get their huge plane to halt before it was too late and land it on the runway. The aircraft landed at midnight in Brisbane. Following a lengthy landing roll, the aircraft eventually came to a halt when the first officer used reverse power and maximum brakes. The 14 crew members and 215 passengers were all safe. At this juncture, the captain summoned the flight's ground engineer into the cockpit. He informed them of the issues they had faced, and the engineer made the connection right away. Leaning out, he opened the captain's cockpit window and saw that the red tags were really dangling from the pitot tubes. The Australian Transportation Safety Board launched an inquiry into the event that lasted for over 4 years. They thus offered many suggestions meant to stop such occurrences from ever occurring again. It was advised that Malaysia Airlines implement protocols wherein ground engineers record any instances in which pitot tubes are covered while on the ground in the tech log. Because the captain signs off on the tech log before each flight, there is less possibility that pilots and ground workers would overlook this crucial piece of information before takeoff. Additionally, they suggested that Airbus update its software to identify unstable airspeed during takeoff and issue an audible and visual alert. This would have facilitated the pilot's recognition of a significant issue that required an aborted flight. All flight crews received a flight safety advisory from Malaysia Airlines after the incident, which advised them to be extra watchful during exterior walkarounds and to make sure that all sensor covers were taken off before to take off. Fortunately, incidents like Malaysia Flight 134 are uncommon. Thanks for hanging out. If you liked this, hit that like button, and don't forget to subscribe for more awesome content. Keep the good vibes going. Check out our next video right here, or dive into more with the playlist below. See you soon.